Today topic is the phase shift. As we know that the total scattering cross section is given by sigma t, that is equals to 4 pi upon k square summation L twice L plus 1 sin square delta L. In this equation, delta L represents the value of phase shift of Lth partial wave. When delta L equals to 0, the scattering cross section will vanish. The maximum value of cross section sigma will be at delta L equals to plus minus pi by 2 plus minus 3 pi by 2 and so on, because you know sin delta L at plus minus pi by 2 plus minus 3 pi by 2 is either plus 1 or minus 1. Since the radial wave functions RR is given by is limit R tends to infinity AL upon KR sin KR minus L pi upon 2 plus delta L, or we can say RR equals to A JL R KR. So delta L is the phase difference between the asymptotic form of the actual radial wave functions and radial function J L K R in the absence of scattering potential. For value of R approximate equals to E or equals to 1 upon K, the phase shift is maximum, and for A is very less than 1 upon K, it will be very small. Now, how to calculate the delta L, or we can say the dependence of delta L on VR. As we know that the equation for the radial part of the wave function for the scattering problem is given by d square psi L upon dr square plus k square minus ur minus L into L plus 1 upon r square psi L. If potential ur is equals to 0, then the equation must corresponding to a free particle solution. That means d square psi naught L upon dr square plus k square minus L into L plus 1 upon r square psi naught L equals to 0. Because we considered here ur equals to 0, then psi L reduces to psi L naught. Now multiplying this equation by psi L naught and another equation by psi L, and after subtracting them we get psi L naught, this equals to this one, and d upon dr psi L naught psi L dot minus psi L naught dot psi L equals to ur psi L dot, and now integrating this equation we get psi L naught psi L dot minus psi L naught dot psi L equals to integration over dr of ur psi L naught. Now for asymptotic behavior, means when r tends to infinity, psi L approaches to sin k r minus L pi upon 2 plus delta L, and psi L naught tends to sin k r minus L pi upon 2. The LHS left hand side of this equation 4 becomes, after solving, that is equals to minus k sin delta L. Therefore we can write minus k sin delta L equals to integration ur psi L naught dr, or we can write sin delta L equals to minus 1 upon k integrating of ur psi L naught dr. If potential ur is considered very weak, then we can say psi L approaching says to psi L dot, and the phase shift will be very small, and sin delta L can be written as equivalent to delta L, or that is equals to minus 1 upon k ur psi L naught squared dr. And now psi L naught equals to kr j L kr, or delta L can be written as minus k ur j L square r square dr, or therefore we can write delta L equals to minus 2 mu k upon h cross square VR j L k r square dr. Thus, if potential is negative, that is means attractive, delta L will be positive, and others and it will be negative. Now, the next topic is the optical theorem. As you know, the scattering amplitude at theta equals to 0 is given by f theta equals to 0 equals to 1 upon k twice L plus 1 PL cos of theta, exponential iota delta L sin delta L, or we can write again this as using Euler theorems, exponential iota delta L equals to cos delta L plus iota sin delta L, or then we can say f theta at equals to 0, 1 upon k summation L twice L plus 1 cos of delta L plus iota sin delta L sin delta L. Because PL cos of theta equals to 0, it becomes 1. So we can write the value of 1, and there will be no change. Now since we know sigma t cross section 4 pi upon k square twice L plus 1 sin square delta L, then we can write the imaginary part of the equation 1. Imaginary part is equals to 1 upon k summation L twice L plus 1 sin square delta L. Therefore we can write sigma t equals to 4 pi upon k imaginary part at 0. This relation is known as the optical theorem or Bohr-Perlius plus Jack formula, and it relates the imaginary part of the forward scattering amplitude at theta equals to 0 to the total scattering cross section. Thank you.